This week's lecture will be about sampling and inferential statistics, and we'll talk about how to actually create a sample from a population, and we'll go into certain tests you can use for inferential statistics. So just to give you a reminder of what a population and sample are, a population is everything within a group that you're interested in. So it's all entities, all objects, all features of any sort of group that you are looking at. Whereas a sample is a subset of that population. And a sample will never have as many objects, entities, or features as the total population. So two examples of this. One is the average height of a human in Canada. Since you didn't specify an age group, that would include every living person living in Canada. And the sample of that could be anything, but one example would be to email 1,000 people randomly in the country to get the average height. The second example is if you're looking at soil moisture level in Toronto. The population would be all soil across Toronto. And obviously that would be impossible to sample every single piece of soil in Toronto. So a sample could be a 20-gram soil sample that you took from each city block. So anywhere in the city block there was a piece of grass or soil, you could sample that, and collectively that would be your sample for the city. So as I kind of alluded to in the last example, why do we need to actually create samples? Why can't we just use the entire population? Well, there's kind of three main issues why we can't sample or can't access data for an entire population. The first is logistics. Sometimes it might be just frankly impossible to gather data from everyone in a population. So for example, testing all of the soil in Toronto, that's not possible to sample every single inch of soil in the entire city. So you have to create a sample. The other thing that might be an issue is traveling to places. So say you were looking at a population where you wanted to interview people on a certain subject. Well, to travel to everywhere in Canada would be impossible to talk to every single person, so you would have to take a sample. And there are many more logistical reasons why you might not be able to gather information about an entire population. A second issue is funding. So oftentimes researchers are funded by governments, or you might have to gather data for a company and there's a budget attached to the project. So certain types of samples are more cost effective than others. For example, if you were to send a mailer out to all of the people in your population, it would start to get very expensive very quickly if you consider a stamp costs about 10 cents. So if you were trying to send a mailer out to millions of people, that's a lot of money. And often it is far too expensive to gather data on an entire population. The last thing is accessibility. It might just be impossible to physically access the location desired to gather an entire population's data. So for instance, if you were looking at a population of trees in a certain study area, it would be impossible maybe to scale a mountain to access the data of a tree that was higher up or in an inaccessible area. This also might be kind of social constructs rather than physical barriers, in that you might not have the permission to gather data from a certain person or a certain area in the environment. There are obviously other examples of this, but these are kind of the main reasons why you have to create a sample rather than using population. So the main goal of your sample is to represent the entire population. Ideally, you would want data from everyone in your population, but because that's not possible, you want to create a sample that represents the opinions or characteristics of the entire population. So there's something called sampling bias, where you are either consciously or unconsciously favoring some segment of the population more than others. So an example of this would be if you were trying to answer the question, do people like Marvel or DC superheroes more? And for convenience sake, you thought, well, let's go to the movie theater. There's a Marvel superhero movie showing at 7 p.m. I'll just wait outside and ask people as they come out. It'll be a convenient way to create this sample. The problem is that because these people actively went out and purchased a ticket to see a Marvel superhero movie, when you ask them, do you like Marvel or DC movies more, you're more likely to have people say they like Marvel movies because they just watched that movie. So with sampling, you are trying to still represent the general public or the general population, whether that be people or inanimate objects. So with sampling, there have been many different techniques developed over time, and the main ones that we're going to go over in this lecture are simple random sampling, systematic sampling, stratified sampling, and cluster sampling. So the most basic type of sampling is called simple random sampling, where you are essentially just taking a random subset of that population. So this is often done with a computer that can actually create a true random sample, because humans find it very difficult to create a random set of values or a subset of population. So in this example, the people in the population have a 33% chance of being selected for the sample. So in this type of sampling, you are assigning a numeric value to the different individuals of the population, and then you're selecting every kth element from a population. So for example, every third person in your population you'll select for your subsample. The good thing about this is you can sample fairly evenly throughout a population, and it's often easier to do than a random sample because, as I said, you need really a computer to create a random sample, whereas you could do this by hand. But the disadvantage is that in some cases you might lose sampling precision. So for example, if you're looking at weather over the last 50 years and you took one weather measurement once per year, you're obviously not taking an average of the entire year if you're just looking at one day in the winter per year. The next technique of sampling is called stratified sampling, and as the picture shows, you're taking your population and you're dividing it into a certain number of categories of your choice. These could be characteristics that you're looking for. And basically from there, you are then trying to randomly select a number of features, objects, or people from each category. The issue with this is that the categories have to be very similar in that the characteristics of each entity, feature, or person in the category have to be homogeneous. So they have to have the same sort of characteristics. And the advantage, though, is the this method of sampling can be a very accurate way to sample a population. You can create a sample that's very representative of the total population. The last type of sampling is called cluster sampling. And this is similar to stratified sampling, except once you've created your categories, you are just simply then selecting all of the people, objects, or features in that category, and you're using it in your sample. You're not going into the categories and then randomly sampling from there. You're just conveniently taking an entire group randomly from that set of categories that you've created. The advantage of this is that it's much easier to implement than the stratified sampling technique that I just discussed. But again, the disadvantage of it is that your clusters that you create or categories have to be very homogeneous so that you're representing the total population well, and you're going to avoid sampling bias. Although these are different types of sampling techniques, many studies in research will actually use multiple types of sampling techniques to access a very representative population. And depending on what type of research they're doing, it might actually make more sense to use multiple different sampling techniques. So the example I have here is if you're studying the personal experiences of immigrants in Toronto, you might first stratify the population by ethnic group because you're interested in the differences between ethnic groups in Toronto. And then you might use the cluster sampling to pick neighborhoods in Toronto. And then you could use the simple random sampling to select houses within those neighborhoods. So some of the issues you might encounter with the different types of sampling techniques are things like ethics, personal safety, permission, and missing data. And those are things that I sort of discussed at the beginning of the lecture, where I was talking about ability to access certain data, and also the costs and logistics of creating a sample, as I also discussed before. And of course, with sampling, when you're creating the actual data set that you're going to be using for analysis for whatever research you're doing, if you've created a bad sample of the population, so your sample is not representative of the population, you're stuck with that data, and bad data leads to bad research. So it's critical that you sit down and you really think about your sampling technique that you're going to use before you go out and collect data and potentially waste money by taking a bad sample. So next up, we're going to go through the actual real methods of testing a hypothesis. So the first thing we need to do is identify the null and alternate hypothesis. And then through the actual analysis or the stats that we're going to do, we can understand and determine whether or not we should accept or reject the null hypothesis. So as a reminder, the null hypothesis, which is sometimes shown as an H with a subscript 0, is essentially the fact that there is no difference or change, or that there's nothing different about the two groups that you're looking at. Whereas the alternate hypothesis, which is often shown as an H with a subscript capital A, this is essentially your actual hypothesis that you're trying to test. So you're saying there is some sort of difference between these two groups, or there is change happening. So there are 5 main steps of hypothesis testing. Obviously, when you're an experienced researcher, you're not doing these steps individually. You're probably doing a lot of these at once, but for the purpose of learning how to do it, it's important to do these steps in order. So the main 3 ways of testing the difference between 2 groups of data is through a difference of means test. So the z-test, t-test, and chi-squared test are all types of statistics that allow you to determine if there's a difference of means between 2 groups of information. And you can go over these different tests and see what the assumptions are about them, but I'm going to just move on and we'll discuss it as a part of the example. So the first example I'm going to go through is a z-test, and just the nature of learning what these tests do, you wouldn't determine your statistical test that you're going to use before you actually start your research, but this is just an example. So if you're wanting to understand if the mean commute distance for people living in Mississauga is different from the mean commute distance for people in Ontario, in this example specifically, you could use a z-test. So if you're given the information about commute distance, that the population would be Ontario, because that is what we're looking at, the mean commute distance for people living in Ontario. So if we have the average commute distance for the population, which is 9 kilometers in this case, and we have the standard deviation of the population, and that is 1.5 kilometers, I would just note that realistically for this question, if you were trying to answer this question, there's no way you would know the average commute distance or the standard deviation of commute distance for the entire population of Ontario, because there's no way you could know the commute distance for every single person living in Ontario. However, this is just an example, so we'll continue on. Your sample then is just people living in Mississauga. So if you know the size of the sample is 225 people, and the average commute distance for people living in Mississauga is 9.3 kilometers. So our first step is to state the null and alternate hypotheses. So the null hypothesis is that there's no change, or there's no difference, that the mean commute distance for people living in Mississauga is the exact same as people living in Ontario. And you're probably thinking, well, we already know from the last slide that the commute distance is different. Ontario is 9 kilometers, Mississauga is 9.3 kilometers. So what do you mean that, how could we ever think that there's no difference between those numbers? We're looking at the statistical significant difference of the two. So it could be that, well, Mississauga's looks longer, but it's not actually longer. There's a random chance that what you found is not actually statistically significant. So that's what we're looking at specifically. The alternate hypothesis is that people in Mississauga have a different commute time than, or a different commute distance than people commuting in Ontario. So since you didn't specify that you're looking for the difference that Mississauga is longer, or a longer distance commute, or that it's less distance than Ontario, you're just saying that you think Mississauga people have a different commute distance, that it could be less or more. That means your alternate hypothesis will use a two-tailed test. So when you actually do the z-test, we're going to be using a two-tailed test because we don't care if it's greater than or less than Ontario's commute distance. We just want to know if it's more or rather if it's more or less. We don't care which way. For step 2, we need to choose the appropriate test, and I'll explain now why we're choosing the z-test. So we know the population parameters. We know the mean and also the standard deviation of Ontario's commute distance. We know that our data is ratio data because it is distance. And we have a sample size. And we have a sample size that is greater than 30. So based on those parameters, we know that we can use a z-test. And the z-test is, the formula is shown there, but we will go through it. And the z-test formula is shown there, and you can see it's 9.3 minus 9 divided 1.5 divided by the square root of 225, which equals 3. So our z value is 3 standard deviations right of the mean. And we know it's right of the mean because it's a positive value. So the next step is to select a level of significance. So I talked about before, so the alpha level or the p-value, no one really calls it the alpha value. It's much more often spoken about as the p-value. So just take note of that. And the p-value essentially represents the probability of committing a type 1 error. So in other words, committing a type 1 error would mean that you rejected the null hypothesis. So you're saying there would be a difference between commute distance. However, in reality, the truth is that there is no difference between those two values. And that comes down to the probability of seeing that level of difference between the population and the sample. So traditionally speaking, a p-value can be set to different values. And traditionally, people would say, well, a p-value of 0.05, which is 95%, is fine to use. And I'm not saying it's not fine to use. It's just that ideally you would want to set the p-value much higher. So either 0.01, which is 99%, or 0.001, which is 99.9%. So the lower the p-value or the higher the percentage, the more you can actually trust your result. And you're probably thinking, well, 95% accuracy is like really high. Why would you need anything higher? Let me put it into perspective. So if you're in a scenario for some reason where you have 3 knife throwers and they have a big target that you can stand on, and the knife throwers tells you, well, I'll pay you $1,000 to stand on the target and I'll throw 20 knives at you, and I'm not trying to hit you, I'm just trying to hit just beside your body. There are 3 knife throwers, and the first knife thrower says, well, I throw at an accuracy of 95%. What does that actually mean? It seems really high, but if your life is on the line, let me tell you, 1 out of 20 times that person's going to hit you with a knife. The hit rate is 5%, so 0.05. And when you have those kind of odds to be hit with a knife coming at you, 1 out of 20 times is really bad odds. That is scary. Knife thrower 2 says, well, I throw with an accuracy of 99%. Already, that increases your chances from 1 out of 20 all the way up to 1 out of 100 times that they'll hit you with the knife. So in this case, the hit rate is 1% or 0.001. 0.01. So already knife thrower 2's accuracy is only 4% higher, but the odds of being hit by a knife are 5 times less likely. And the knife thrower 3 throws with an accuracy of 99.9%. And that would be 1 out of 1,000 throws will hit you with the knife. So in this case, the hit rate is 0.1% or 0.001. So again, knife thrower 2 was 5 times less likely to hit you than knife thrower 1, but knife thrower 3 is 10 times less likely to hit you than knife thrower 2. So you can see, although there's only a few percent difference between 95% and 99.9%, the actual chance of being hit is so much lower. It's so significantly lower. And it's the same with statistics. You don't want to commit a type 1 error because it is basically saying that there is a difference when there's not actually a difference. And you want to be using the highest level of p-value you can use. So yes, sure, in research, people still use p-value of 0.05, but I would argue that is much too low to commit a type 1 error. So from here on out, we will use a p-value of 0.01 because I think personally that 0.05 is far too high of a chance of committing a type 1 error. So in step 4, we will look up the critical values and compare our test statistic to the probability of committing a type 1 error. So because we're using a two-tailed test, that means we don't care about the direction if it's higher or lower than the population. So you can see in the picture there on the bottom is a color-coded distribution where it's showing you what is significant. So 0.01, 0.05, 0.1. That shows you the area under the curve where it is significant. So since we're using 0.01, the critical value or z-score that is associated with that value is 2.58 standard deviations. So in step 5, we can interpret the findings that we just found through the z-test calculation as well as the critical value that we found. So if you recall, the z-value was 3 standard deviations right of the mean. Our z-score that we just found was 2.58 standard deviations. And our null hypothesis is that the mean distance of commuting is the same for Mississauga and Ontario. Our alternate hypothesis is that Mississauga people have a different commute distance than people living in Ontario. Thus, based on the fact that our z-value of 3 is greater than our z-score of 2.5, we can reject the null hypothesis and we can state that Mississauga's average commute distance is different than Ontario's average commute distance with a significance of p less than 0.01. In example 2, we'll look at a situation where you would use a t-test. So the second example is asking, do loggerhead turtles in our study area weigh more than the general population of loggerhead turtles? So we know worldwide that the average loggerhead turtle weighs 135 kilograms. But unfortunately, we don't know the standard deviation. The sample that we've taken, and we're looking at a specific study area, The sample is 10 turtles. The average weight of these 10 turtles is 150 kilos, and our standard deviation is 40 kilograms. So the first thing we do is state our null and alternate hypothesis. So our null hypothesis is simply that there's no difference in weight between our study area and our population of loggerhead turtles. And our alternate hypothesis says that loggerhead turtles in our study area weigh more than turtles worldwide. So in step 2, we'll choose our t-test for the following reasons. The main thing is we don't know all of the population parameters. So we don't know the population's standard deviation. We do, however, know our data is ratio, and our sample size is less than 30 because we only have 10 turtles. We also know that we want to use a one-tailed positive t-test, and we know it's one-tailed because we only care about turtles in the sample weighing more than the population of turtles. So if we wanted to know if the turtles were a different weight than the population, so if they're weighed less or weighed more, then we would use a two-tailed test. But because we only care if the turtles weigh more than the population average, we're doing a one-tailed test. So because the t-test requires more calculations, I've put it on a separate slide here. And you can see for yourself, you can go through the numbers and the calculation to see how we're deriving these values. But the resulting t-test value from our example is 1.13. So now we want to select a significance level. And as I explained in the last example, a p-value less than 0.01 is the significance level that we should be using. And then step 4, we want to look up the critical values and compare that value to our test statistic. So for a t-test, we don't use the z-score table. We use a critical values of a t distribution. So it's a different distribution, thus it's different values. So based on this chart down below, we have on the y-axis the degrees of freedom, which I'll show you in the next slide. And then on the x-axis along the top, we have our one-tailed and two-tailed significance levels. So we want a one-tailed test with a p-value of 0.01. And then we have 9 degrees of freedom because 10 turtles minus 1 is 9. So 9 degrees of freedom. So that intersects at 2.821. So that our t-score value for this data is 2.821. So degrees of freedom is kind of an odd concept, but it's a mathematical concept. So I'll just give you an example and hopefully you'll understand after this. So degrees of freedom represents the number of values in a calculation that are free to vary. So this is all based on just basic algebra. So if we know the sample size, in this case will be 4, so just 4 numbers, and we know the mean, so in this case it's going to be 10, we could have 3 numbers, and those 3 numbers could be any numbers, and we would always know the outcome of the last number based on the mean and based on the sample size. So let me just go through that. So if we have raw values of 7, 8, and 14, and then the 4th number we don't know, based on a mean of 10 and a sample size of 4, we can calculate for x. So we do x plus 7 plus 8 plus 14 divided by 4. And that equals a mean of 10. So if 10 is then equal to x plus 29 over 4, we take the 4 from the right side And because it's being divided by on the right side of the equal sign, we bring it over, multiply 10 by 4, which gives us 40. So 40 equals x plus 29. And to bring the positive 29 over to the left side, we would do 40 minus 29 equals x. So then we know x is equal to 11. X can't be any other number other than x based on that information. So, okay, we found out what x means. How does that make sense? How are the other three numbers allowed to vary based on that result? So we can change those first three numbers and we can always find the value of x. So let's change the initial three values we know, so 7, 8, and 14, and we'll do -10, +5, and +20. So now we have the mean is equal to 10 is equal to, in brackets, x minus 10 plus 5 plus 20, and then divide that by 4. So we take the mean of 10, multiply it by 4, because we're bringing the divided 4 over to the other side. So now we have 40 equals x plus 15, and then 40 minus 15 equals x, so x equals 25. So in this case, or really in both cases, we know the mean is 10, we know the sample size is 4, and we know 3 of the 4 raw values. And in both cases, it didn't matter what the raw values were that we knew, we could always solve for x. So the 3 numbers of the 4 are free to vary. Thus, degrees of freedom is equal to n minus 1. So 4 minus 1 is 3. 3 numbers out of the 4 can always vary, and you'll always know what x is. So that's what a degree of freedom is. So in step 5 of our t-test, we need to interpret our findings. So our t-value is 1.13 standard deviations right of the mean. Our critical value for p less than 0.01 is positive 2.821. And thus, based on our t-value is less than our critical value. Thus, we cannot reject the null hypothesis. So we found that the loggerhead turtles in our study area do not weigh significantly more than loggerhead turtles worldwide. Okay, so in our last example, we're going to go through how to do a chi-squared test. So in this example, we want to know, is the occurrence of natural springs influenced by the rock type? So we have the picture there, and we've summarized that information from the picture or the map into a table. So we have rock type, so we have limestone, calcareous marl, and sandstone. And then we have the number of springs per rock type. So limestone has 7, calcareous marl has 3, sandstone has 14, and we have a total number of springs of 24. So to state the null and alternate hypothesis, the null hypothesis is that there's no difference between the observed and expected frequencies. And our alternate hypothesis is that there is a significant difference between the observed and expected frequency. So in other words, if we have 24 total springs, you would expect the number of springs to be evenly divided between the different rock types. So if the null hypothesis was true, it would be that each type of rock would have 8 springs, because 24 divided by 3 is 8, so there should be 8 springs in each rock type. So the alternate hypothesis is that no, rock type does influence springs, and thus each rock type won't have 8 springs. So step 2 is to choose the statistical test that's appropriate, and in this example we're using chi-squared. And the reason we're using chi-squared is because, first of all, we know the observed and expected frequencies. So in the original table, it showed how many springs were in each rock type. And because we know the total number of springs, we can divide that by the rock type to determine the expected number of springs per rock type. And the last thing is we're using categorical data, so chi-squared is the only test we can use of the 3 that we're showing. So this is also the formula that we use to calculate the chi-squared. So it's the sum of the observed minus expected springs, square that, and then divide it by the expected number, and that gives you the chi-squared statistic. So here I've summarized all of this information into a chart so you can easily understand how to calculate it, and it also shows the observed number of springs, so the 7, 3, 14, versus the expected frequency, which is 8, 8, 8. And then it shows the calculation as well as the chi-squared, the total chi-squared statistic. So in step 3, we are choosing a significance level, and because we're using a chi-squared distribution, that's what the distribution actually looks like. And in the chi-squared distribution, you'll never have a negative value because the distribution starts at 0. And the distribution of chi-squared is dependent on your sample size, or more specifically, your degrees of freedom. In the case of a chi-squared test, you can't test the direction of the relationship, so you can't see if something should be less or more than. You can only test whether it is the same or is not the same. And as I've mentioned in the last 2 examples, we'll use a significance level of p less than 0.01. So as we did with the z and t tests, the chi-squared distribution also has its own set of critical values. So our degrees of freedom in this case is 2, because we have 3 rock types, minus 1 is equal to 2. So if we look at 2 degrees of freedom and we're looking at the significance level of 1%, that means our chi-squared critical value is 9.210. So then we can interpret our findings. So our chi-squared statistic was 7.75. We calculated that. Our critical value is 9.210. And based on those 2 values, since our chi-squared test statistic was less than our critical value, that means we cannot reject the null hypothesis. So rock type does not significantly influence the distribution of springs within the study area. Even though it might look like it does, statistically speaking, it doesn't. So this is the R tutorial for the sampling and inferential statistics lecture. I will go through the different types of sampling that you can do, as well as the inferential statistics. And I, in this tutorial, zoomed in a little bit on the window, just so you can see a little bit better. So just view and then zoom in if you want to do that. First thing we want to do is load the libraries and import the data. The data set we're using today is the IMDb movies from there. Has a lot of different variables. So it's the ID that's associated with the movie, title, original title, year, genre, duration, so on and so on. And this tutorial, I'm not gonna go through the code as much, at least not the stuff that I've already taught you in the past, because I'm assuming now that you've done and gone through a bunch of the tutorials that you're on the same page as me in terms of basic functions like the filter function, for instance. Okay, so the first sampling technique we're going to go through is simple random sampling. This is really easy. There is a function that was created for this exact reason. So our movies data frame has over 85,000 movies in it. And say we want to select 1,000 random movies. We can use this function called sample_n. It takes a data frame and then a number. And this is the number of movies or the number of rows or observations you want to select. So let's go ahead and run that. You can see over here it's created this data frame, and there are 1,000 random movies that were selected from the original population of movies. So the issue with the sample_n function is that because it's random, every time you run this code, it's going to select a different sample of movies. So let me show you what I mean. So in this for loop I've created to show you that the sample is changing each time, I have I in 1 to 10. So I is going to start at 1 and then iterate to 1, 2, 3, 4, 5, all the way to 10. So it's going to run this block of code 10 times. And it's going to essentially just do this function. So randomly select 1,000 movies. And in order to check if the sample is changing, we're going to print off the mean of the duration. So the duration represents how long the movie is. So if the sample was the exact same each time, you would expect the average duration of 1,000 movies to be the same every time, because you're taking the mean of the duration of the same 1,000 movies. Now, if the sample is changing and it's selecting different movies each time, you'll see that the duration or the average duration of the 1,000 movies will change every time. So let's go ahead and run this with Control Enter. You can see down here in the console that the duration of the movie, or the duration of the 1,000 movies that were sampled, are different every time. So this tells you that this sample_n is selecting 1,000 random movies every single time you run it. So you're wondering, why am I telling you this? The reason is, if you are doing research and you were randomly selecting 1,000 features, people, objects, whatever from your population, and you did that and you created some statistics based on that sample, and then you didn't finish your analysis and you came back to it and reran the analysis, all of your numbers will change. Everything you did will be different, and that's bad, really bad statistics. Like, you should never do something like that. You should never take a sample of a population, run statistics on it, and then change it later. There's several reasons for that. Obviously, the main one is that because you're changing the sample, it comes off as you didn't like the result of the first sample, so you're taking a second sample to get a better outcome that aligns better with your information. or your desired outcome. The other reason you don't want this to be random every time is because if you send your code to a different researcher in your group, or if you publish the work and someone requests the code, they should be able to run this sample_n function, and it should give them the exact same sample as you had. So you're probably wondering, well, okay, how do we create a random sample that doesn't change every time you run the code? There is a function called the set.seed. So this is a set.seed function, and it takes one value, and the value can be anything, but it just needs to stay the same. So the set seed essentially works, so random number generators in pretty much any computer software, anytime you're creating a random number or a random event, it's often based on the clock of your computer. It can be based on different things, but in R at least, random number generators are based on your system time. And specifically, I believe it's looking back to January 1st at 12 a.m. in 1970, and that is essentially 0 seconds. And then it's your system time is however many millions or billions of seconds has passed since that date. So it's then anytime you're creating a random number, it's adding in the system time into the calculation. So every time you create a random number, as long as you're creating it every second or every millisecond, it is generating a new number because the time is changing every time you run the code. So that's what's happening behind the scenes. And that's why it's important to set a seed if you're creating a random sample. So now let's go ahead and run this. So when you run it with the set seed, it gives you 100.332. We run it again, the exact same number. Now if we do a for loop, same as the one before, where we want to run this block of code 10 times, we'll go ahead and run that. You can see 100.332. Same sample of 1,000 movies every single time. And that's really crucial if you want to produce the same sample every time. Now, let's look at what it means to change the value in the set seed. So this is the exact same function, or for loop rather, as this one. It's just that the set seed up here is 1, 2, 3, 4, and down here it's this number right here. Now we run it. It's a different sample, yes, of course, because we used a different set seed. However, crucially, all 10 values are the exact same. So we know when it took the sample, every time it was using the same set seed value, and thus it created the exact same sample every time. Now let's look at what if we change the set seed every single time we created our output sample. What would happen? So this function, or this for loop rather, is still going to use 1 to 10, but what happens is the set seed is going to be the function or addition of 1. It's going to start at 1 and add I. So in the first iteration of this for loop, it's going to be 1. I is going to be equal to 1, so 1 plus 1 is 2. And then the next time it iterates through, the I is going to be equal to 2. So the set seed is going to be 1 plus 2, which is 3. So the set seed is going to be changing every time. And the same goes for this print function. Let's go ahead and run this. And you can see the set seed value is 2. The mean duration is 99.491. The set seed value is 3. The average duration changes. And you can see as it loops through all 10 numbers and the set seed value is changing, the sample that's being created, the 1,000 movies that is being selected, is changing every time. So that's what a set seed does. And that's also how to create a simple random sample. So let's move on to systematic sampling. This is a little bit more tricky. So systematic sampling is when you're taking every kth number in a sample. So every fifth object, person, entity, every 100th, and so on. So let's select every 100th movie to create a sample. So we're going to use a set seed. And then we're going to create a data frame called systematic, input the movies, and filter using this math right here. And I'm going to explain the math after I create the data frame. So in order to use the set seed, you have to actually select all of the code to run it. So the systematic data frame was created, and you can see it. Well, you can't exactly see what happened, but you can see that it has selected 858 movies, which makes sense because 85,855 divided by 100 is approximately 858. So how did we actually do that? The filter function, the condition of it is row underscore number. So row number, if we look in the systematic data frame, row number refers to this column. It's not technically a column in the data frame, but it has a list of numbers from 1 all the way down to, in this case, 858. So the row number is essentially just a unique identifier that is associated with the data frame, but it's not technically a variable in the data frame. So this is a type of division. If you think back to elementary school, when you were learning how to divide, you would have learned how to use long division. And long division tells you essentially how many times can this value go into this other value, only with whole values. So you're not going to have a fraction. And then the remainder left over from that, you'll have as a secondary thing. So let's look at, so this condition is the row number modulo, which is what the 2% signs mean. Modulo 100 is set equal to 0, so a remainder of 0. So it's going to do row number divided by 100, and it's going to do that for every single row, and it's only going to select rows where the remainder is 0. So let's look at a different example. So this is a very basic example, 5 modulo 3. So let's look at the answer of that. So if we look at down here in the console, it's a 2. Why is it a 2? So 5 divided by 3, 3 can't go into 5 more than one time. So 3 goes into 5 once, and there is a remainder of 2. And there's a remainder of 2 because 3 plus 2 is 5. So 3 goes into 5 once as a whole number, and then it can't go fully into 5 again because there's only 2 left. So 5 modulo 3 is equal to 2. So if we did 7 modulo 3, take a second, think about what the answer might be. And now we will see what the answer is. So 7 modulo 3 is 1. And it's 1 because 3 goes into 7 2 times, as a whole number. So 3 plus 3 is 6. So 3 goes into 7 twice. And then there's a fraction left over, and it's 1 remainder. So 3 goes into 7 twice, and that's 6. And then 7 minus 6 is 1, so there's a remainder of 1. So 100, or let's do 200 modulo 100. And you can see in this case the remainder is 0 because 100 goes into 200 twice and there's no remainder. There's no fraction left over. So this is what this filter function is based on, this condition. So if we want to select every 100th movie, we want to only select when the row number modulo 100 has a remainder of 0. So 100 went into each row number a perfect amount of times. So hopefully that makes sense. If not, you can look up what modulo or these percent symbols mean and look up other examples. So now let's look. So we have the systematic sample completed, and we're going to look at the mean of the duration. And we're going to do this to see if the sample is the same every time, just like we did in the last one. Let's go ahead and arrange the movies. So if we wanted to arrange one of these variables, so sort them highest to lowest, and then see what happens. So we're going to sort the systematic data frame by duration, and then, or we're going to sort the movies data frame by duration, and then create a sample. And we'll see if the mean of the duration changes. So is the sample changing? And you can see in the console, the first sample was 98.8, and this second one is 100.3. So we know the sample actually changed, but why did it change when we sorted the data? It's because the row number is not static, basically. This row number changes based on the data frame, the state of the data frame. So when we sorted the data and created a new data frame, it rearranged the row numbers because the row numbers aren't static with the actual data set. They're not directly associated with the data frame. They are secondary, and it's more of an RStudio thing for RStudio to identify rows. So let's show you how to then create our own identification number for each movie and how we can use that to then create samples that we can control. So let's go ahead and in the original movies data set, we're going to create a new column called ID_num, so ID number. And we'll set it equal to 1. We'll start at 1 and we'll go, this colon means we're going to create a range. We're going to start at 1. And we're going to use n row of movies, which will create n row of movies will output 85,855 because it's just telling us that there's 85,855 rows in the movies data set. So effectively, this here is just saying we want to create an ID number field and fill it with values 1 through 85,855. And the benefit of using this is that you don't have to worry about making a typo about how many numbers or how many rows are in the data set. You can just use n row and it'll know. So let's create that. We'll look at the movies database, or data frame rather. Scroll to the end. We have now an ID, unique identifier of every movie in the data set. So if we just scroll down a bit, you can see there are numbers, and that's good. So every movie is now uniquely identified. These are also unique identifiers for each movie, but we can't use these for the calculation, the modulo calculation. We can't put in TT0009 and divide it by a number. It wouldn't work. So we need our own ID column that are numeric values. So let's go ahead and now create the same systematic sample, but instead of using the row number, we're going to use our ID number column. So you can see ID number, we just created it, modulo 100, remainder 0, and we've now created I'm just going to slide this over. We've now created a new sample using our ID number. And you can see ID number that this systematic sample actually was a success because it starts at 100, goes 200, 300, 400, 500. And you can scroll down and see that every 100th movie was indeed selected. Now, the reason we created this ID number field to uniquely identify these values is because now, based on the ID number field, because we've created an ID column or variable that is directly associated with the data frame, we now can sample independent of the sort of the data. Let's calculate the mean of this. So it's 98.8. Now let's arrange. We're going to arrange the data, so we're going to sort it by duration. And then we're going to take the ID number modulo 100 and select only every 100th movie. And we're going to take the mean to see if it matches the previous mean of duration that we just calculated. And you can see, even though we've arranged or sorted the data, it's still giving us the same mean duration, which means it's still selecting the exact same sample as it was in the other one, despite sorting the data frame before creating the selection. Let's open this data frame that we just created. And you can see the reason it has worked still is we look at duration. It is indeed sorted from highest to lowest, but the reason it still was able to select it is because these ID numbers are directly associated with each movie in the actual data frame. So you can see the ID numbers aren't sorted anymore, but it still was able to select every 100th movie. And to kind of reiterate this idea, if we were to arrange the data by some other variable, so let's say we arrange by the number of votes, it's still going to give us the exact same value. So it's still giving us the exact same sample. We can sort this data however we want. We can arrange it, blah, blah, and our sample is always going to stay the same. And again, this is really important for research. If you're working with this data a lot and you're going to be sorting the data, you're going to be doing different things with your data, and you should always have the same sample. So that's why it's important to either use a set seed for random number generators, but in this case, it's not based on random chance or a random number generator. It's just based on the original data set, but we don't want to base it on row number. We want to base it on a static ID number associated with each value, or each movie rather. Okay, so moving on to stratified sampling, we're going to first categorize the movies by decade of when they were created. So 1960, 1970, 80s, 90s, 2000s, 2010, blah, blah, blah. So we're going to take advantage of another math function called floor. Floor takes a value, and instead of rounding it in the traditional sense, so 5 or more, it rounds up, or 4 or less rounds down, it always rounds the number down to the nearest 1. So if we take the floor of 1989, it's still 1989 because 1989.0 rounds down to 1989.0. Now let's take... The trick is to round 1989 down to 1980. We first have to divide it by 10. So we have 198.9. And then we can take the floor of that to output 198 and then multiply it by 10 to create 1980. Let's go ahead and let's run just this code. So 1989 divided by 10 is 198.9. Then we take the floor of that value, creates 198, technically 198.0. And then we take the floor of 1989 divided by 10 and then multiply that result by 10, which equals 1980. So that's how we're going to select movies based on the decade, by using this trick. So in this case, we're going to be using set seed, and this is just a random number that I came up with. It doesn't matter, it's just that you're using the same number every time. I'm going to create a new data frame called stratified, input the movies. We're only going to be looking at movies that were made in 1950 or above. And we're going to create a new variable called decade, and that's going to be set equal basically to this. But instead of 1989, we're just going to input the year. So the year's obviously going to change based on the year the movie was actually made. And then we're going to group by the decade. So this is where the stratified sampling comes into play. Actually, you know what? Let's run this code and then you'll see what the decade actually is and how it relates to the year. So let's look at stratified. We'll look at, so the year of this first movie, the first row is 1983. We look at the decade, it's 1980. We look at the next one is 2001, and the decade is 2000. I'm sure you understand how decades work, but the math behind it is what's creating that classification. So now that we have a data frame where we have a decade indicated by movie, so once we've created the decade column, we can then group by the decade and input it into the sample function, where we're going to take 100 movies per decade. And then we're going to use the ungroup function at the end just to return the data frame back to its original status. And the ungroup function isn't always necessary, but if you go in and try and use the data frame again for something else, it might give you errors saying, well, it won't tell you that you need to ungroup the data. It'll just give you errors, and you'll be stuck in this rabbit hole of troubleshooting because you didn't ungroup the data. So that's why we ungroup it at the end. If you run the code without ungrouping it, it still works. It's just that the next block of code won't work if it's still ungrouped. So let's run this with the set seed, see what the mean duration is. It's 99.83. So now we're just going to run this code to see if it did indeed work as intended. So you can see this block of code is just counting the number of movies per decade. So we only wanted decades that were equal to or above 1950. And you can see that there was 100 movies selected from all decades in our population. That's good. It worked. Awesome. So now let's look at cluster sampling. So the first thing is we need to have a list created of all the decades that are available, because the code required to create a cluster sample is a little bit more complicated. So decades, and then we'll create a sequence. So this is going to create a sequence of numbers based on what you tell it with the arguments. So it's going to start from 1950, and the sequence is going to go all the way till 2020 rather, and it's going to iterate through these values by a value of 10. So it's going to start at 1950, then go to 1960, 1970, all the way up to 2020. So let's go ahead and run that, and we can copy this and paste it on its own line and run it, and it'll show you that it's created this list of numbers. Okay, so I just added a little bit of I added a comment to the last line of this function, just so when you're looking at it on your own, you can understand it a little bit better. So basically what this is doing is you're creating a cluster data frame, inputting movies. We only want movies that were made in 1950 or later. We are going to create a decade variable with the same formula from the last example. And then this is the main difference. So with our filter function, we're going to use this %in% tool. I don't know what you call it. Tool, I guess, or function maybe. We want to select movies where the decade is in or within this sample function. Let's run this sample function on its own and see what it's doing. So basically, the sample function is looking in the decades list that we created. So this is our decades list. And it's looking in that range of values, and it's selecting 3 different years. And it's different years because we're using the replace argument and setting it to false. So f is equal to false. So it's selecting 3 decades, and it's not repeating any decades. So then so if we run this multiple times, you can see the sample that it's selecting is different every time. It could potentially be the same twice in a row, but if you run it multiple times, it's going to be different. So the filter function is then saying, okay, we want to select decades where they're equal to or within this sample. So it'll select rows where the decade was equal to 1970, 1950, or 1960. And it'll do that for every row, and that's how it'll filter the data. So let's run that and look at the cluster data frame, and you can see it has selected 29,139 movies. You can see the decade is 1980, 2000, 1980, 1950, and if you scroll down, you'll see the decades are always in those 3 ranges. And much easier than looking into the actual data frame and scrolling down and looking at it. One way you can definitely confirm that it's only selected 3 decades, and what they are is to use the unique command. So this is a base R function, so you have to input the data frame $ variable, and you can see it has selected 1980, 2000, and 1950. And in this case, the data frame or the sample has 29,139 values or movies. Now, if we run this code without the set seed function, you'll see that these values change every time. And that's because the sample function that is within the filter function, so this sample function, is based on a random number generator. So if we're not using the set seed function, every time you run this, it's selecting a different sample. But if we run this with the set seed function, you can see every single time it's going to be the exact same. So that's really important. Now, as I talked about in the lecture, oftentimes you'll use a combination of different sampling techniques. So here's an example of first stratifying your sample by decade, then clustering to pick a movie based on the genre, and then selecting every 100 movies from that stratified clustered sample. So I'm just going to kind of go a little quicker through this. So this is the stratified sample, and it's the exact same as the example we went through. So I'm just going to run it. And that's going to create the combine _ stratified data frame. And this is just to verify that, yes, it did work. Cool. Now we're going to cluster to pick movies based on the genre. First thing we need to do is kind of clean the data, so the genre data. Because if you look into the combine stratify dataset, and we look at genre, you can see that there's multiple genres per movie. We just, for the purposes of this, want to select the very first genre. So this first movie is a comedy and a musical. We just want to identify it as being a comedy. So the first thing we need to do is we're going to create a new column and use the string extract function. We're going to input the genre variable. And we're going to use this basically to only select the text before the comma. And it's going to not worry about anything after the comma. So I'm going to run that. Now if we look at combine stratified and scroll to the side, main genre, you can see now only has one genre. So cool. Now what we're going to do is create a list of genres. So we're going to use the unique function and create a list of the unique genres. Again, we can copy and paste this into its own line and run it, and you can see in the console it is output a list of all the different genres. So now to actually create the cluster of genres, we will run this code. So quickly again, we're using the filter function, and then we're going to look at main genre, where it's in the sample of genres. So it's the exact same as that other example. And then we're just going to verify that it did what it needed to do using this unique function. So I'm going to run that. It has selected drama, thriller, and animation. Cool. Now the last thing is we want to select every 100th sample or every 100th movie within the stratified and clustered data frame. So the cluster data frame was called stratified underscore cluster. So we're going to use this line of code, which is the same as before, to actually, sorry, we're not doing every 100th movie. We're doing a random selection of 100 movies from the stratified and clustered movies. So we're going to run that. And we are going to use this code to just look at the final data set. So you can see here, these are the decades, and this is showing how many movies were selected from each decade. And you can see it's different for most of them. And then we can look at the genre, and you can see in terms of genres, how many movies are within each genre that was selected. So that's how to do kind of a multifaceted sampling approach. All right, so the next thing we're going to do is go through the hypothesis testing. And in this, I'm not going to go through all of the math and all of the code necessarily, because I'm assuming by this point you understand how to do a lot of this stuff, and you probably don't want to hear me talk about the formulas and how they work, because you can just look yourself in the lectures and compare and do it that way. And then for the assignments, as long as you understand kind of what's going on, you can copy and paste a lot of this and use it for the assignments. And these examples are the exact same as the ones from the lecture. It's just the coding version of it. So the first thing is to create the given information. So we're just creating objects or variables set equal to these values. So we don't have to input the actual value. We can just input the variable. So pop underscore average instead of inputting 9. Our null hypothesis is that the mean is equal to 9. The alternate hypothesis is that the mean does not equal 9 kilometers. Our test is two-tailed. So our z value is set equal to this math equation. You can reference the formula as I just said. So our z value is it's just 3 basically. Our critical value, so because we're using a two-tailed test, our p-value has to be divided by 2. So that's a very crucial thing. I'm not positive if I said it in the lecture, but I'm saying it now. Your p-value, so if it's 0.01, it has to be divided by 2 if you're using a two-tailed test. So that's really important. qnorm is a function that will essentially just output the critical value based on your p-value, and if you want to divide it by 2 for a two-tailed test. If you're doing a one-tailed test, you would just have it like that, just the p-value, and then lower dot tail is equal to false because it's a two-tailed test. So critical value is equal to 2.58. You can see that up in the top right. And now just to test, so is our z value greater than our critical value? We can use this line of code. So the absolute value of z, so if your z value was negative, the absolute function would just multiply it by -1 to make a positive value. And we want to see if it exceeds the critical value. So is it statistically significant? So you can run that. In the console, you can see true, which means that your z value is greater than your critical value. And I've created a little if-else statement to output the result of our state or our condition right here. So if, and then in brackets, you just put this same condition in here. And then the little squiggly bracket. So if this is equal to true, so if this comes out or outputs as true, print off this sentence. And if this output is false, it'll skip over this line of code and it'll go to this else function and it will print off this line of code. So let's run that. And you can see in the bottom, we must reject the null hypothesis. Mississauga's average commute is longer than Ontario's average with a statistical significance of p less than 0.01. Now, as we have done in the past, we can take that code and just input it all into a function. So you can see the z value, critical value, and our if-else statement is sitting within our z-test function. And the z-test function is taking the pop average argument, pop SD argument, sample size argument, sample average argument, and our p-value as arguments. We run this to create the function. So we now have a z-test function, which takes those arguments, as I just said. And now we can use z_test, input our pop average, pop standard deviation, sample size, sample average, and our p-value. We can run that, and it outputs, we must reject the null hypothesis. So that's a really great way to run that that test. And then if you wanted to use different data, you could easily change it right here without writing all that code. So to move on to the t-test, so we just want to know, are the study area turtles, do they weigh more than the population? So here are our givens. We will run that code. Our null hypothesis is that the mean is equal to 135 kilos. Our alternate hypothesis is that the mean is greater than 135 kilos. And our test is one-tailed. So the standard deviation of the population is calculated using the following code. And we had to do that because we didn't know the standard deviation of the population. It wasn't given to us, so we had to calculate it ourselves. Now we have to calculate the t-value. And because this is one-sided, our p-value does not need to be divided by 1. And so this qt function is used to find the critical value of a t distribution. And it needs the p-value, and because it's one-sided or one-tailed, you don't divide it by 2. And then the other argument you need to put in are the sample size minus 1. So this is the degrees of freedom that you're calculating by doing sample size minus 1. And we're going to take the absolute value of that. So it's a positive value. That's how you do critical value for t-test. And then again, here's our condition. So is the absolute value of our t-value greater than our critical value? In this case, it's false, as it was in the lecture. Now, if we put all of that information into a function, and we also have the if-else function inside of our main function, we can run this to create the function. And now we have our t-test function, which takes the population average, sample size, sample average, sample standard deviation, and our p-value. And we can input it like that. And it says we cannot reject the null hypothesis. Now, if you wanted to change any of that data, say, oh, when I was reading the data, I actually misread it, and our sample average is actually 154. Or you did more research and you came back and wanted to use the same function, you could then just change that data and you could run the code again. So in the first case, we're rejecting, or we can't reject the null hypothesis, so there is no difference between the turtles. But if we came back with more data and we found our sample of the turtles was actually 154 kilos, then when we ran the code again, we realized, oh, you know what? The sample turtles are actually, they do actually weigh more than the population turtles. So to move on, this is the chi-squared example. The biggest difference in terms of coding for this is that we need to create a data frame manually using the information from the example in the lecture. So first thing we need to do is create a rock type variable. So rock type is set equal to C bracket and then in quotes to signify that they're text. We have that. So we'll run that. And then the same thing, but with numbers for the number of springs. And just note that limestone and 7 are, there are 7 springs in the limestone rock type, and there are 3 springs in the calcareous marl rock type and 14 in the sandstone. So the order in which you put these values in to the brackets does matter. So if we run both of that, and then we run this, so we're creating a data frame and setting it equal to the data frame function, so data.frame. We're inputting rock type and number of springs. So just we're putting this data together into a data frame. So it outputs as a data frame, which you can see is the exact same as the one in the lecture. So we have our givens, so we know the p-value we want to use is 0.01, and the expected number of springs per rock type is 8 because there are 24 total springs, and we're dividing that by 3 because there's 3 rock types, so 8. The null hypothesis is that rock type does not influence the number of springs. Alternate hypothesis is that rock type does influence the number of springs. So this coincides with the formula that was shown in the table in the lecture slides. So I'm going to run that. And our chi-square is equal to this formula. And our chi-squared critical value is this formula. And I will just say that this q chi, so q chi sq is a function dedicated to the chi-squared distribution. So you're inputting the p-value as you did in the other examples. And then you're inputting the degrees of freedom. So the number of categories -1. So that's your degrees of freedom. And then the lower dot tail is false because it's one-tailed, because it has to be one-tailed, because chi-squared only can be one-tailed. So run that chi-square critical value, and our condition is our x square value, so is our chi-square value greater than our critical value? In this case, we can see it's false, which was the same as in the lecture. Here's our if-else function. We cannot reject the null hypothesis. Now, if we create a function using that, so putting this information into a function, we can run this to create the function. The one thing I will say about this is df, so the data frame you want to use, and then the observed column, which is the number of springs that you actually counted. When you are inputting it into a function, you can't simply just have df $observed column, because R won't understand that your observed column that you're inputting. So in this case, you'll have num underscore spring in quotes. It'll read it as text and it'll be like, what is this? And it won't be able to understand that you're trying to identify a column. So if you put df, so your data frame, and then 2 square brackets, and then you have 2 square brackets on either side of your observed column. And that will tell R, okay, the observed column is actually a column. It's a variable in the data frame that you are inputting. So you run that function, and then when you input chi squared or chi underscore test, and you're inputting rock spring, that's our data frame that we created. This is the column that you're interested in with the observed number of springs. This is the expected number of springs per rock type, and this is our p-value. So if we run that, you can see we cannot reject the null hypothesis. Now, what if you found an error in your study area? There is actually only 21 springs in the area, and you had to change the expected number of springs per rock type to 7, then you could rerun it and it would easily output an answer for you. So if there was an expected number of rock springs of 7, you would reject the null hypothesis. So that's the only stuff we have to cover for this lecture. I think this lecture probably was much easier in terms of the actual kind of coding. If not, go through the lecture and this slowly, and when you're doing the assignment, kind of reflect back on what you learned from this and maybe just rewatch it again. And hope that helps, and good luck.